Assalamu alaikum. In this video, we are going to solve another problem related to gas power cycles, but here we can work with constant specific heats. So I will use room temperature based CP, CV, and K values, okay? Because it's not mentioned that it's variable and temperature range is not too much. So we can use constant values of CP and CVs. Mass is given for this cycle. Okay, so it will be not specific based calculations. We should also find the kilojoule values. So we have at the beginning you can fix your entropy like it's a datum point, reference point. Doesn't mean how much entropy you have. Just fixed to 0. Isentropic compression from 100 kilopascal. So you have 100. And your initial temperature is given, as you can convert it to Kelvin, and second pressure is 1000 kilopascals. And you have heat addition is given for 2 to 3, but you have constant pressure, so that means for state 3 you will have the same pressure. We don't have state 4 for this cycle. This consists of 3 states. Then you come back to state 1 again. And you have here pressure is a linear function of volume. So we will show it on the graph and how we will use that information to calculate the work. Okay. So let's start by first process. Okay. First thing what you can do is just fill your table if you can use ideal gas law or table or any calculation. So this is what is temperature 1 is 300 over pressure 1. So you will get 0.86. Okay. Actually, U values you can find it by CVT. Okay, CVT is just equal to U, so you can find them like this: CVT1. And CV values will be based on room temperature values. So this one times temperature, you can easily get this value. Let's use red color. Okay. Second one, when you go to second state, you just focus on your definition of this process. It's isentropic. So you can use isentropic relations, which is like this for specific constant heat ratio, specific heat ratios, constant specific heat ratios. So here 300 pressure ratio, just put the values. Then K is 1.4 from the table, you know it. So you will calculate 10 to the power 0.4 over 1.4. That will give you the second temperature, which is 579.2 Kelvin. And specific volume can be easily found from the ideal gas law. Okay. Okay, 0.17. U is calculated from CVT2. Okay. Actually, we will not, we can need some of them. So let's calculate all U values. T2 is this one. So 9. Okay. We have from 1 to 2. You can calculate the work, or last thing to do here is just calculating the using the first law. So from 1 to 2, the heat addition is equal to work done, and that's just minus work done is equal to the internal energy change. But these are specific values. We can multiply them by mass, but for now we don't. Maybe we don't need for now. Just when in case of need, we can use. Is it so? It's isentropic compression, and work done from 1 to 2. Isentropic compression. Okay. So this is 0, right? Isentropic means adiabatic and reversible. So you can only just easily get the work 1 to 2 is equal to just U1 minus U2 if you flip this signs. So U1, this is U1 and this is U2. So there will be negative work. That means system is not doing the work. The work is being done on the system. Let's calculate this. That will give us a negative value, which is kilojoule per kilogram. For now, let's keep it like this. Then if we need something else, we will use. From 2 to 3, you have constant pressure heat addition, and you know the amount of heat. Okay, 2 to 3. If you know this Q from 2 to 3, you can say, I'm using big signs now. So it will be U3 minus U2, okay? From here, you can actually get the temperature. You have constant pressure heat addition. If you send these guys to other sides, Q2 to 3 will be equal to U3 minus U2 plus work done. And work done is here for constant pressure, which means P times delta V, right? And that will be equal to just enthalpy change. Just the enthalpy change from 2 to 3, right? So from there you can calculate, like this is 416 kilojoule, which is equal to M times delta H, specific enthalpies. So 0.5 times T3 minus T2, and you know T2, right? T2 is, we calculated is like this. So here you can calculate T3 easily from the calculator or just by hand solution. You have X, you don't know this value, minus this value, so you can say shift solve, then you get the value. So our temperature is going to increase to 1411. We calculated that, and you can also from there you can say CVT, you can find this value. Actually slightly large amount, not so specific heat assumption is not good for this problem, but in the question is not, it's not stated to use variable, so feel free to use, even it will give some error, but acceptable for this kind of like learning purpose. But if you have if you are working on a project, so be careful, you will just use real values, table values, or any engineering database values. So now actually we can calculate V from the ideal gas law. So 0.40, right? What about this internal energy? You can calculate it from CVT. But I think we will not need, I don't know, we will see. For like Q input, Q output, we have already have Q input. So Q, yeah, I think we are gonna need this value. Okay, so now the last process from 3 to 1 will give you the heat rejection value, okay? So heat rejection, let's say Q from 3 to 1 minus work from 3 to 1 is equal to U3 to 1, right? And we are searching this value, heat rejection, because calculate the heat rejected, one of the problem parts, and we have constant pressure heat rejection. So it's a linear function, so you can get the average and calculate, or alternatively we can before calculate this work, you can do it by integration, or from the plot you can get the area. So if you want, let's finish part A, then we can easily calculate the work done from the area of the curve. So let's finish part A. Okay, we have TS diagram. Initial entropy is 0, and second entropy, we need to calculate it. Okay, let's calculate entropy change. Here it's isentropic, it's 0, but from 2 to 3, okay, let's skip this. Let's move this part down, and we missed something here, we skipped it. It's delta S from 2 to 3. It is just using constant specific heats, you can say Cp ln T3 over T2 minus R ln pressure ratios. Okay, so we know the values, we can calculate directly. Go to the table. So Cp, which is 1.005 times ln of the pressure temperature ratios, then minus R times ln of the pressure ratios, which is 0, which is 1. ln 1 will give you 0, so it's only 0.89. So delta S just 0.89. So you can say your big entropy value is already calculated. Here is 0.89. You increase the temperature, your disorder, your entropy value is increasing. So what about temperature values? We have 3, let's say here 300, we have 579, then we have 1011. At the beginning, you have 0 entropy and 300 degrees. This is the one. Then you have isentropic process. You increase your temperature during the compression. So this is 2. Then you come back to, you come to this point, 3. So it's going to be like this. Then you are coming back to point 1. So the process cycle is just only 3 points. It's like this. And what about PV diagram? For PV, we have only 2 pressures and 3 specific volume values, 17, 40, 86. 17, 40, 86. At the beginning, we have, okay, so 100, 0, okay, so we are here. Then we have, like we are increasing the pressure, isentropic compression, so volume, specific volume is gonna decrease, right? So it's second point is here. So you have something like this. Your first process is something like a curved path, something like this. And third point is just specific, constant pressure heat addition when you expand, when the gas is expanding by constant pressure heat addition. So you have something like this. Then you come back to this one when you have linear curve, okay, linear straight line, you have constant slope. Where do you know it? From where do you know it? You know it from here, because it's mentioned that it's a constant. So C1 is a constant, like slope of the curve. So you can easily calculate the work from the area under the curve, right? But here we have specific volume values, so that will give us I'm sorry, let me take the pen. Okay, constant pressure values. Pressure to a specific volume graph will give you the work, right? So here you have a constant slope, this line, so you can just calculate this area. Okay, so it's area of the rectangle plus area of a triangle. So this area, just specific work from 3 to 1, is just equal to this area 1 plus area 2. So area 1 is just basically volume change times the pressure, right? 100 plus this one is just 900. You have the height, 900 height over 2, height over 2 times base. So base is again is gonna be the volume change, volume difference. Okay, so let's find the volume. So it will be 253 kilojoule per kilogram, and we are going to write. That means this is a positive work. Okay, this work is gonna be done by the system. So you put here positive values. So Q31 is equal to U1 minus U3, or you can say mass times U1 minus U3 plus mass times the work, which is 200. This minus will gonna like convert to plus when you send the other side. Okay, so 0.5 times U1. U1 is this value minus U3, right? Then you have plus mass times the work done. So you should get a negative value, kilojoule. This is the heat rejection, okay? And so I think we calculated what we need. We just drove the plots, and we have the heat rejection for part B is calculated. This is the heat rejection. How do you know if you don't have any other heat rejection? Here Q is 0. From TS diagram, if you have constant entropy, no heat release. Here you have Q input, and here you have Q output. So your heat rejection only from 3 to 1. And you calculated that, so that's okay. You only need to calculate for part C the thermal efficiency. Thermal efficiency is like work net over Q input. And work net is just Q input minus Q output, right? Rejected heat. Yes, you are adding some heat, then rejecting some. So the difference between them will give you the net work. So it is basically 1 minus the ratio of the heat out minus heat out over heat input. So 1 minus heat input is 416 over the amount that we calculated here. So that will give us the efficient. I'm sorry, we flipped. Here you have this value, then hit Q out. Okay, so that will give you a percentage of your efficiency, which is 34% of thermal efficiency you have. That's all for this problem. See you at the next video. Thank you for watching.